You can go back and watch any of these talks from the past. We cover different tech subjects, and the month of August, we meet on the second Thursday at 3 p.m. And on August 10th, we heard a talk by Bob Simons, who is the principal developer of ERDDAP. And you can go back and watch that presentation. If you tried to watch it before, we had a problem with the audio and video syncing, which we have reworked, and it's now in sync. So if you struggled with that, you can go back and watch that again. So that Bob covers sort of what ERDDAP's all about and where it's going. Really nice talk. But we thought it would be fun today, 2 weeks later, to have folks from the community talk about how they're using ERDDAP. And so one of the kind of cool things that always happens at the SciPy Scientific Python conference that I go to every year are these 5-minute lightning talk sessions at the end of every day. And so it's kind of where I got the idea for this. And so posted it out on the Google group, which if you don't know, there is a Google group for ERDDAP, and everybody you can sign up there. Posted it out there, and a number of people said, hey, sure, I'd love to do that. So we've got 8 people signed up for today. And so the way it's going to work is I'm just going to make each person on this list in the order that you see here. I'm going to make them the presenter, and they're going to give a 5-minute talk. And I'm going to cut people off after 5 minutes. I've got my stopwatch open here. And that way we can make sure that we get to the end and we don't run over, and we have enough time to ask questions. So we're not going to ask questions during the presentations, obviously. Even clarification questions we're not going to ask. We're just going to go right to the 5 minutes. And so I hope that this should be fun. And we've got a bunch of different aspects of ERDDAP that are going to be shown. So without further ado, I think I am going to make Jen Savagian the speaker. And the most challenging part of this for me is going to be finding the speaker on this long list of people. There's 42 attendees, folks. That's great. So Jen, you should be unmuted, and now I'm going to make you the presenter. And as soon as we can see your screen, which you can please share. Okay, looking good.
Okay.
All right.
Oh yeah, so you can hear me?
Yep.
All right. I'm Jen Savagian, formerly Patterson, and I'm going to show some tools today that visualize real-time data from ERDDAP for different Senkus and Polar Watch projects. The first one is this oyster conditions dashboard, which is used by oyster farmers to provide them with real-time information about environmental conditions that can impact their crops. This has interactive time series, plots of upwelling water temperature, and other environmental variables that can impact oyster farm operations. So they use this in like a real-time capacity to just see what's going on out there, and they can look back at data for, back in time to see how things now compared to how things used to be. So this is all built with JavaScript and pulls data straight from ERDDAP and plots it all in the client. This tool has helped build relationships with farmers, has helped us learn more about their needs, and has led to additional collaborations with sensor development and in other regions with additional farmers. The second page is just a dashboard page for real-time in-situ observations. This is an operational tool used by the people that maintain these sensors and serves as an entry point for people looking for in-situ observation data, and links back to ERDDAP for people to download data. These dashboards are basically all built with JavaScript, and I've posted some fiddles, so if you're interested in this sort of thing, you can test out bringing in data from your ERDDAP just by changing out a few lines of code, and these are available online for people to test out if they're interested in that sort of thing. The next interface is Centu's El Nino page, which is like a user engagement and communication tool that pulls ERDDAP data in and was displaying it for you know, the year that we had the El Nino here, and we're generating some statistics that kind of offer like a gee whiz, look at that, try to engage people with the data. If they're interested in it, they can learn more about where the data came from. And the ultimate goal is to get people to read articles about what the scientists are seeing in the California area during the El Nino year. More recently, been working on building an interface that sits on top of ERDDAP and provides previews of ERDDAP satellite data sets in polar projection for a new project called Polar Watch. So this interface is fed by ERDDAP. It offers basically just a custom view of our Polar Watch ERDDAP server, which looks like that. And it uses the standard ERDDAP RESTful API to search and populate with metadata and to actually download data. The next page. So it provides these kind of data previews, the similar ERDDAP data subsetting, just with a different look and feel. So this is in development right now and would be available on GitHub in the fall, and there'll be a version that does this without all the projection stuff as well. We've been doing a lot of user engagement as part of Polar Watch and developing tools and training for them on how to access data from ERDDAP. And so we're posting tutorials related to how to extract data, like for a region of interest or along animal tracks and that sort of thing. And those are posted on my GitHub and available on the Polar Watch website. And if I have time,
I think that's it though. Thank you, Jen. All right, we're gonna move it along. That was awesome, and we're gonna move it along to Jim Patemra, and I'm gonna make you the presenter, Jim, and you should be able to share your screen.
Yep.
All right, and go ahead.
Okay, this is Jim Patemra. I'm at the University of Hawaii. We use ERDDAP for mostly through our PAC-IUs, our regional association work, but today I was going to show you very quickly a different use, and this is with our cable observatory. So we maintain a site called ACO, which is about 80 miles north of the island of Oahu. We have a bunch of instruments sitting on the seafloor, cabled back to shore. And one of the things that that has become popular with Tsunami Warning Center and others is our pressure gauge. The pressure gauge is presenting data at high frequency in real time. It goes through the bottom-mounted sensor, then the fiber cable to a shore station, to a local server, and then we're using NC to listen to the port on the server. And then we just create a bunch of ASCII files, and then we use ERDDAP's table from ASCII files, our service, and then pump it through HighChart. And just to show you an example of that. Oops. So here's our ERDDAP server, and this is all the PAC-IUs data. But I'm talking right now about this this one right here, the bottom pressure recorder, and it's a little snippet of code that uses HighChart. I guess this is a lot of people are using HighChart. I think Jen, you were using the same thing, where we're pulling this, we're making use of this now minus 1 minute. Whoops. Now minus 1 minute feature from ERDDAP to get us some real time. And here, hopefully looking at the real-time display coming off the bottom sensor. So this is bottom pressure. It's about 4,000 meters down on the seafloor in near real time. Every second we're getting data. So that's kind of a cool thing. The other thing I wanted to show in my 5 minutes here is, and this is just recent, we have a hydrophone down on the seafloor as well, and this is extremely high frequency for sort of the typical OBS. It's 96 kilohertz, and what we're doing right now, because to be honest, we don't know any better, is we're making these 5-minute wave files. And I talked to Bob, and I was like, I want to be able to aggregate these things and do some operations across files. And as a first step, what we've done is put these in ERDDAP. And now we're looking at this line right here. So this is our hydrophone, and there's a link on files, if you can see that as a file source. And the solution that that Bob came up with and we were able to enable is to make a table from these file names, and then a data set that lists the file names. And note here that we should include some notes in these things to identify sounds, and that way we can search on these things. And then we add a base file URL. So if you were to click on that file link, you get a page like this, and then you can just click on a file, and it'll open this with a I'm just going to use QuickTime. Or slow time. There we go. And it'll open this WAV file, and off we go. And like I said, ideally we'd want to be able to add metadata into these files, because I don't know if you can hear these whale vocalizations and such. But that's a next step down the road.
We can hear them.
Excellent. It's not my pre-lunch stomach noises. These are. Okay, so I'm going to stop there.
All right, great. Thank you. That was different. And let's see. Next up, we have Connor. I will unmute you. Connor, are you there? Connor? Hello, Connor. Are you there? Maybe we'll come back to.
I'm here.
Oh, you are there. Okay.
Yeah, sorry. Can you see my screen?
Yeah, not yet. I've just made you the presenter, and now you can. You should be able to share your screen.
I have it shared now, so can you see it now?
Looking good. Yeah, go ahead.
Okay. So greetings from Ireland, where it's actually sunny at the moment, which is amazing. So I just wanted to give you a quick talk about how ERDDAP had impacted on work that was being done in the European Commission. To give you just a brief overview, the European Commission is the civil service arm of the European Union. And in Italy, they have a vast campus that is dedicated to policy research and policy support based on scientific work. So in a few years ago, when we had problems with piracy off the coast of Somalia, the JRC, the Joint Research Centre, was tasked with looking at this problem and trying to come up with an analysis of it. And I went down there to work with them. When I arrived, they had built a global ship tracking system for tracking ships using sensors on the ships called AIS sensors. But they had nothing else in this for trying to figure out what the ships were doing. They had no weather data, they had no ocean data, nothing like that. And I was tasked with the job of doing this for the team. So the problem we have in Europe is similar to the problem which we have in NOAA. We have data centers all around Europe, and trying to bring all the data together into one place is a major headache. There's a big project called EMODNet going on in Europe at the moment, and there's another project called Copernicus that's trying to do all this. And they are doing well, and they are now getting to the stage where we're now able to access these data sets through web APIs. But they're nowhere near ERDDAP. And I had come across ERDDAP when I worked at the Galway Marine Institute here, and we were working on a research project called Envirify, which is also funded by the European Commission, and it was looking at the future internet. We were future gazing on how we could access environmental data using web architectures, and we came to the conclusion on that project that the cutting edge was ERDDAP. We said that in our report, and we used it to make a very simple dashboard of Galway Bay. And the big advantage for us for using ERDDAP was that it allowed us to develop things quickly and cheaply. So when I came to the European Commission, the JRC, I sort of showed this type of technology and said, this is what we need to do. And I met it with a lot of resistance because there was a certain amount of, well, we're going to be using American data, we're not going to be using European data. And the taxpayer is paying for the European data, so we should be using it. And I pointed out that if we use ERDDAP, we'd be able to get done in 3 months, something that would take us about a year to do. So we knocked up a very quick ERDDAP server where we brought together all the marine science data sets from around the world that were useful for maritime situational awareness, and we put it onto one server. And then from that, we used that as our go-to point to get the information we needed. So here we have a scene off the coast of Somalia, where in the top left-hand corner we have wind, and in the right-hand side we have waves. And down the bottom 2 panels we had what would have existed before, where we had no auxiliary information. And we were able to identify very quickly that the times when there was no piracy were times with high wave heights and high wind speeds. And we were able to advise shipping accordingly and the coastal support off the coast of East Africa. So we were able to quickly determine what problems, what situations the piracy was occurring. And we were able to do it very, very quickly because we used ERDDAP to pull in the data we needed. And we were so successful in this that later in the project, we were asked, could we look at the Arctic? Because there was lots of concern about the climate change opening up the Arctic routeways. And once again, we just went straight to ERDDAP. We went to the RTOFS datasets, and we were able to pull out the ice model data for the Arctic and stick it into the system. I can't show you any shipping here because that data was classified, but I'll just show you the type of map we were able to create. And then we were able to determine which ships were icebreakers and which ships weren't icebreakers, and provide us with a lot of contextual information we wouldn't have had before. So the point I'm making here is that ERDDAP opened up all this scientific data that allowed us to do things with it, and it provided in a way that it could be easily used by non-scientific community, non-scientific software development community. And the main data sets we're using were the global forecast system, WaveWatch 3, and the real-time ocean forecast system. And the success of ERDDAP in doing this and sharing data around has taken off in Europe, and now EMODNet itself is starting to use ERDDAP to share data. So it really is hitting the zeitgeist and becoming very, very popular. So that's this.
All right, Connor, thank you so much.
Thank you.
That was fantastic. All right, next up we have Kevin OBrien. Kevin, you are now the presenter. Yep, looking good.
Let's see. Can you see my screen?
Yes, we can. Now we can't, and now we can. And you're going to go to present mode?
Yes.
Yeah, okay.
Okay, great.
Looking good.
Thanks, Rich.
Actually, it's not in present mode yet.
Oh, yeah, sorry. 2 monitors, it confuses me.
There we go. Thank you.
All right, thank you, and thanks. I'm happy to be part of this ERDDAP Palooza event we got going on here. It's fantastic. I want to talk a little bit higher level about some of the ways we're using ERDDAP and how it's kind of a linchpin in some efforts to improve integration and access to various global ocean observing networks. And this work that I'm involved with is being done through the JCOM Observations Coordination Group, of which I'm a member. And just to thoroughly bore everybody, I just thought I'd put a definition of interoperability up there just so we're on the same page. And this definition, which talks about the ability of tools from non-cooperating resources to integrate, is really applicable to what we're doing in this effort to integrate data from the various disparate ocean networks, because they are definitely non-cooperating resources. And yet integrating those data is crucial to understanding the processes that are happening. And so we're talking a couple of broad categories of integration. One is collecting within a single observation network, for example, drifting buoys or Argo floats. You have a bunch of different separate floats, but you want to, often look at that data set as a collection of data rather than individual features. And then there's the sort of a cross observing system look, which is being promoted in order to understand the essential ocean variables and essential climate variables. And that's obviously a much more complicated process. In both cases, as I mentioned, we're looking at ERDDAP as the solution for that. But in this presentation, I'm just going to kind of focus on the first category of a single observing system. And what I'd like to do is look at the University of Hawaii sea level data as a case study for how we're using ERDDAP to improve this access, and doing this in cooperation with Phil Thompson and Derek Young and Mark Merrifield out at the University of Hawaii Sea Level Center. They have a bunch of tide gauges that are measuring sea level. They actually do a great job with their data. They have NetCDF CF compliant data, and they have it available in a thread server, so you can access it through a thread server. I mean, the only issue with accessing it through the thread server is then you're sort of looking at individual tide gauges and sea level from those tide gauges, so it's not a collection of information. And if you kind of drill down into the data a little bit more, what you see in those NetCDF files is you don't see sort of a discrete parameter that identifies each individual tide gauge. So they have the time and the space and the depth and the sea surface height, but there's no parameter that is something that for CF you need as a time series ID. And this is where ERDDAP shows its flexibility, because one of the goals of this this project to integrate this data is that the people that have already created data files don't have to recreate those data files to meet some sort of requirement to get to be more interoperable. And so one of the things that ERDDAP allows you to do is to use attributes. So in the global attributes for those tide gauges, we can see that they do have individual IDs provided for each station, and those are unique for each station. The cool aspect of ERDDAP that allows us to utilize this is that in the ERDDAP configuration, we can then use that global attribute to promote it to an actual data variable. And that means that we can then define the CF role of time series ID that's required in order to stitch this whole collection of tide gauges together. And so that means that within an ERDDAP server, we've seen some examples, but now we have the whole collection. We can still look at each individual tide gauge if that's what a person wants, but because we have the ability to look at a collection, we can look at the whole collection. And this also means that we can then, and I'm going to actually try to show a little demo here, we can actually hook up higher level access services, which we've seen from the previous presenters, which are really cool, to get to that ERDDAP data, get to that ERDDAP server, and create visualizations and discovery tools. So in this case, we see the various tide gauges. We look at the whole thing as a collection, and if we're interested in the time series of several of them off the Philippines, we can go ahead and select those and ask for a time series plot, and we'll get the time series from all of those platforms plotted together. So now we can look at the collection of observations contextually within the scope of each observation. So that's really a power that ERDDAP provides us for that. And so back to the presentation here, that's really all I wanted to say. We are using ERDDAP in a multitude of other projects. It's the linchpin for the Surface Ocean CO2 Atlas Automation Framework, which has allowed us to go from multi-years of a release to now we do yearly releases and could even do 6 monthly releases if we wanted to. There's a Betty proposal that got funded to update access for global drifter data. There's a really cool open access to GTS project that I'm involved with, which is using ERDDAP to both help put data onto the GTS, but also get data from the GTS. There's some new sail drone missions that are going on here at PMEL, which is this new platform. We're using that to integrate ERDDAP to integrate that data. And also, again, I mentioned EOVs, and that's an ongoing process. And I think that's all the time I have. So thank you.
Awesome. Thank you, Kevin. Love those ERDDAP sheets. Yeah. Okay, so now it's over to John Kerfoot. John, you should be able to share your screen. Beautiful.
All right, can you guys see me or hear me and see me?
We're looking at GitHub.
All right, so what we wanted to, we set out a few years ago, IUS and a couple other partners set out to sort of figure out a way that glider operators could submit or provide a very simple NetCDF format that was not necessarily CF compliant. And then what we would do is we actually, in talking with Bob Simons, he had suggested that if you use a very simple format, you can use ERDDAP to basically do a whole bunch of the heavy lifting in terms of the aggregation and making things CF compliant for you, right? So we're working with this dynamic of we want as many providers as we can get. But we also don't want to put all these restrictions on them or try and enforce all of the, enforce a bunch of different things on them where we wouldn't get a lot of cooperation, or the cooperation or the number of providers wasn't what we wanted. So what he had suggested and what we ended up coming up with was a very simple, for the gliders, essentially what you've got, right, with the glider, you've got a glider moving through X, Y, and Z space also in time. So it's essentially a trajectory, which is a time series. But in talking with a lot of the users of the data, particularly in terms of assimilating it into models, what had always been in place was we want profile data. So we've got a glider going through the water and it's running through time, but what we really want is to be able to identify profiles and assimilate profiles and look at things on a profile basis. So we had come up with actually a 2 ERDDAP server solution where we had asked the providers if they could submit data and just a very simple on a profile by profile basis. So what we have is, we look at here, so this image that I have here, right, kind of displays in terms of glider terminology what we've got. So we've got a glider goes in the water and you have over a deployment or a trajectory. When that glider, the time between that glider dives and when it surfaces is as a segment, what we'll call a segment. That segment is made up of a bunch of different dives, where a dive is a down profile and an up profile, and then we divide those profiles or those dives into individual profiles. And so the unit that we're dealing with here is the individual profile sort of unit, right? And so what we decided to do was use a what we'll call a private ERDDAP server, which accepts individual NetCDF files that constitute a single profile from a glider. And then that back-end private server takes those individual profiles and aggregates them into a trajectory profile NetCDF file data set, right? So and then using that backend server, we have a front-end public server that basically makes calls to that backend server for the aggregated deployment, or all of those profiles that make up a trajectory, downloads that as a single multi-dimensional, let me see here, we've got, let me go back. So this is a kind of a simple schematic. Up here is basically what the data providers are responsible for. So they take their raw data files, they break them up into individual profiles, a pretty simple NetCDF file format. They submit those via FTP, and then what we do is we use the private ERDDAP to aggregate those into either a contiguous ragged array trajectory profile or a multi-dimensional array trajectory profile. And those are served by the public ERDDAP server. And so what ERDDAP has allowed us to do is on two ends. One is it does a lot of the heavy lifting in terms of the aggregation and the CF compliance and all that sort of thing. It's also provided a front end, right? So a data service or an API that allows us to build things. We have a status page here for the ERDDAP, which allows us to sort of take a look at what's available, number of profiles, the times things have started, time things have ended, threads links, all that sort of stuff. So there's an API that we can go to and we can build web displays on. And then obviously we have, this is the DAC ERDDAP site. So if I take a look at, I just want to show a couple things here. So
your 5 minutes are up. You want to just wrap up real quick?
Yeah. So I won't go through the graphing or the plotting, but essentially what it has allowed us to do is provide users with the ability to search for glider data and look at it on a profile basis and also a time series basis, and provide an API that allows people to develop a lot of front end sort of services that we feel are useful to the community.
Awesome. All right, thank you, John. And we're gonna skip over to Stephanie Pattillo, who, let's see here. I'm gonna make you the presenter, Stephanie, and you should be able to share your screen. Looking good. We're looking at the IT&I GoToMeeting screen, and now perfect.
See that?
Yep, looking good.
Okay. All right. So hi, I'm Stephanie Pattillo. I'm at Woods Hole Oceanographic Institution. I'm working with the Ocean Observatories Initiative group here, and the problem that we're using ERDDAP to solve is what you're seeing here is a screen for an old display that we had. We have a bunch of moorings with these strange names down the left side of the screen, and we needed a way to display what's essentially right now a snapshot of the status of all of our moorings, which is a screen full of stuff. And we have some plots currently, but all of our files are individual daily files. So what people have had to do in the past is go into our server, download these files day by day, and then aggregate them on their own with MATLAB or whatever. And as you can see, there are tons of files for this is our wave instrument right now. And so we have, these are all ASCII files, and then you need to parse all of those and plot what's going on. So we decided to build a better system for this with an ERDDAP backend. So we've used Python to parse and process all of these data and to parse and process them in somewhat real time. And so you can see our ERDDAP server now has all of these moorings worth of data for all of these instruments. The one we're looking at here is this Wave SS instrument. And so we use that. Obviously, you can plot it and access the RESTful API down here in order to pull that information out. And so we're using that as a backend right now for a user interface, which is built on Django, accessing our ERDDAP server here, and then and then based on that system, we have a SQL database in the background that deals with some of the metadata, and then we've built this new user interface that has so this is currently some of our moorings, so this is currently in development. But if we're looking at here, the same mooring with the Wave SS data. So here we have the buoy, and these are lower nodes down on the water column. And we can plot up our Wave SS data, not just from the last 24 hours, but from the last 12 months. And so this makes a huge difference for us because now we can aggregate all of this data together, plot it up, and we're working on tools so that we can actually, you can print the images, download the data as a CSV so that you don't have to go through and aggregate all the files yourself. So that, in a nutshell, is what we are working on. This is very much in development at the moment, but it solves a huge problem that we've had so far with our mooring operators not being able to see what was going on with our instruments and with the data. And this also allows us to do statusing on all of our instruments and the data coming off of them so that we can see whether or not things are working properly. And that's mostly it.
All right, awesome. Thank you, Stephanie. All right, and over to Charles Carlton. Let's see, I'm going to make you the presenter. And you should be ready to share your screen. Perfect, looks good.
Okay, so my job is not to study the data through ERDDAP. My job is to set it up to make it easy for other people to use and to get as much of NCEI's data available through easy access methods such as ERDDAP as possible. So one interesting thing about a lot of this is climate data. So we have ocean models, weather models, climate data records, and models specifically for studying climate. What you see here is the climate forecast system, and you see it's in the ice thickness in the polar regions. Now, the interesting thing about climate is how things change over time. So I'm going to switch to this handy Havmahler, or time versus another axis diagram that ERDDAP enables. So for example, the x-axis is time, the y-axis is latitude, and the latitudes are near the pole. So what you can see is you can see this striping pattern that is the annual ebb and flow as ice gets thicker and gets thinner as it freezes and melts. And then you can visually see this overall pattern showing how it's getting thinner over this period of 1980 to 2010. So another example with climate is they're concerned about land use. So here's a land cover map. Sorry, I've got an interruption here. Okay, land cover map that is showing different types of vegetation. We might be interested to see how this varies over time. So I picked one type of vegetation, which is boreal evergreen needle leaf forest, and I picked a set of latitudes around Canada and picked times, and you see these times go way back into the 1800s, before 1800. And you can see how the density of the forest changes as in the north it's beginning to fade away. Another big long data set is sea surface temperature. Here you can see this is on the 180th parallel over the entire latitude range over time from the 1800s to now, and you can see this stripy effect of the annual variation. Now, this data can be very complicated, and the model data can have a lot of things, and they have dimensions such as air pressure, isentropic levels, etc. To create these databases in ERDDAP, you could have one data set that you're trying to build to have this just sort of explosion of different data sets. And another problem is that sometimes the data, you think it's going to work with ERDDAP, but it's got glitches that interfere with ERDDAP, and you need to know what is going to cause trouble and how to deal with it. So I made this thing called the inspector, and what you see is an overview of the stuff currently running in ERDDAP. And for data sets that break into different pieces, like for example, this isentropic variable height data, you'll see that this sort of overview, and it shows that it had to be broken up into two data sets, one of which is by isentrope latitude and longitude. And then you'll see another one that's pressure surface, temperature surface by latitude, longitude, and time. In other words, two-dimensional and three-dimensional. This program split that out, made a description for me, and it also generated the XML for the datasets.xml. Now, it can all seem wonderful, but sometimes your timelines, there's some missing data, and it can be hard to know where it is just by looking at threads. So this inspector will let me see a calendar showing which data is missing. And I picked one that was too long. And yeah, hold on.
30 seconds.
Oh, right. Well, one thing we have to do is we have to look for trouble. So if the timeline has duplicates or goes way into the future, this report will actually let us check to see if the timeline is good. So this one, it will show the sequence of time, how many steps there are, and that you don't see any trouble here. But this one, it will actually show me that it has sometimes steps that are 0. So basically it shows us start, end, and the number of time steps and how big the steps are. And if you have time steps that are 0, ERDDAP doesn't like that. So this timeline will not work with ERDDAP, and that's a warning to the data set. This has also notified me that due to GRIB index lookup errors, this data has a forecast going out to 2148, which being that it's like a 5-day weather forecast is obviously incorrect. So this tool lets me quickly find problems that will prevent stuff from working in ERDDAP, and I can go and check the data and try to correct the problems.
Awesome. All right. Thank you, Charlton. All right. And finally, we have Eli Hunter. Eli, I'm making you the presenter, and you should be able to share your screen. Looking good.
Can you hear me?
Yes, we can.
Okay. So yeah, my name is Eli Hunter. I work at I'm with Rutgers University, and I work in the ocean modeling lab there with John Wilkin. What I'm going to talk about is a little bit different. You know, there's most of what's come before has been using ERDDAP to provide services to outside users, which we do as well. But some of the most useful things that we've developed has been for internal use. So one of our major ongoing projects is a real-time forecast, data simulative real-time forecasting model for the Mid-Atlantic Bight area, which is built in ROMs and over what we call the espresso domain. You can see the domain in the second panel there. It says OBS latest SST. That's our espresso model domain. The thing that happens is that we have a lot of disparate data sets that are going into this this model forecast, this simulation and forecast. There's observations, obviously, of sea level, SST, water velocity.
You can point with the mouse.
As well as forcing, atmospheric, and point sources. So you can imagine if we're running the model every day and something happens, something doesn't look quite right, we might want to go back and see what's happening. Was it an input file? Was it an observation? Was it was it one of the meteorological forcing files? So what we did is we used the ERDDAP slide sorter as a way of just building a panel that gives us at a glance, in this case for the last 7 days, what all that data looks like. So going from on the left here, SSH, which we get from a variety of altimeters, sea surface temperature, which comes from both remote sensing and in situ, CODAR from the Rutgers CODAR system, and of course CODAR is only surface velocities, and then whatever in situ data we can pull off of the GTS through the OSMC ERDDAP server for our particular region. I'm going to go quickly look at the data set for our observations. What's really nice is that the way our observations files are set up is that we can sort things by a type. In this case, it's they go from 1 through 7. Actually, it's 1, 4, 5, 6, and 7, where 1 is sea surface height. So you can see all the tracks since the 23rd of August for the satellites that are going into our data simulation for models for the past model runs for the past week.
Obviously, we can do that for 6 is sea surface temperature. Of course, since we have both AVHRR, or sea surface temperatures, remote sense sea surface temperatures, some gridded sea surface temperature products, and in situ data, it's kind of hard to see what's going on. So it gives us the opportunity to sort things by depth, so that we can see exactly what's happening in terms of in situ data, which might have, that's below the surface, which is always much less dense than the surface data for sea surface temperature. Also salinity. So we could go back and look at this and say, there's some problem with their salinity. Is there a bad salinity observation value that's causing it, or is there something else wrong? Outside of observations, we use NAM weather forecasts to force the model meteorology. More than one time, if there's a breakdown in our collection of data from NAM, we'll see something's wrong with the model. We'll come onto this and see one of these screens completely blank, and then we can go back and rerun the data acquisition for our meteorology, and then rerun that particular day's forecast. So we go all the way from air pressure to long wave radiation. And of course, we have river discharge. In this case, we have 7 stations that we call as that is our river input into the espresso model. If we go really quick to the other thing that lets us do, we go to markers, longitude, latitude. We don't pick a particular station, discharge, and we can get a quick picture of all the stations that are going into the model for the very latest data that we have from those models, from that from those observations.
All right, Eli, thank you so much. That was awesome. All right. Well, that's it. What I thought we could do is, that was fantastic. It was really interesting actually to see all the different aspects of ERDDAP. I thought, we didn't see anybody using it in notebooks or with R, like in Python or R or anything, but we could do those like another time. I just wanted to, let me open up, unmute everybody. Actually, Bob Simons, do you have any comments you'd like to make? I mean, you must be feeling pretty good right now.
Yes, wow, those were all great talks, and it's so interesting to see what people are doing and that they're using it so well in so many different ways. So that's just great. One thing I'll say that's coming up in the next version related to Charles Carlton's talk is there's a new response type which returns information about gridded data sets and tells you where.
Sorry, Bob, could you repeat that? I had to mute everybody.
Yeah, just so you know, in the next version, there'll be a new response type which will tell you for gridded data sets where the gaps are in the time series, because that's a common problem we have here at ERD, and I know other people have that problem, and Charles has solved it by himself, but now it'll be in ERDDAP, so it'll give you a little report saying where there are gaps, unusually long gaps in the time series.
That's still useful to me because my program is something I run in advance to make sure there isn't trouble. It's not something that shows up to the user, and this new feature would help the users.
Yes.
Charlton, there's actually a couple questions here about your inspector. Is that what language is it written in, and is it available for others to use? Or is it just your own your personal thing for right now, or what are your plans?
Okay, it's documented well enough that it should be, it's something we could put on GitHub. We haven't really done anything about publishing it. It's in Python, and I designed it to use like batteries included. In other words, I could have been made it easier for me to write by using the netcdf Python, but that's hard to install. So I wanted to make this so I could run it from anywhere. So it's definitely something that could be distributed and reused. We just haven't done anything to publish with it.
Okay. Let's see, there's a question for Jen, I think, on how you made those map projections for the polar regions. I think, Jen, you're muted. I don't seem to be able to unmute you. Okay. Let's see. Actually, does anybody? If you can unmute yourself, Bob, do you know how she made those?
Unfortunately, I don't.
Okay. All right. So somehow.
Sorry, this is Connor here. We had to do polar regions.
Oh, sorry. I'm sorry. I got confused.
Yeah.
So how did you do that, Connor?
So, well, in RTOFS, the real-time ocean forecast system, the polar regions are on a different grid than the rest of the data in there. So that was a bit of a trick we didn't realize at the beginning. So it took us a while to figure out what was going on. So what we ended up doing at the end was downloading the data and using GDAL to convert it into the projection we needed, because the interface to the ocean, the maritime situational awareness system was a web interface. So we had a whole PostGIS server and a geo server and a WebGIS front end. So ERDDAP was the core, like the data source we went to get the files we needed to populate the system.
I see. Okay, that makes sense. Let's see. If you want to ask a question. Oh yeah, sorry. Yeah. Let's see here. So does anybody else have? I don't think I see any other questions in the chat. Does anybody else want to ask a question? Well, I guess I had a question for Jim Pattillo about that ASCII step. It seemed like for real-time data, is that the only option you had? You were trying to get it to the web, from sensor to web, as fast as possible, right?
Yeah, that's right.
And was that just, doesn't that slow you down, or no? It doesn't? No,
it's just a single number, and it's actually processed through the software that comes with the Parascientific.
Okay. And what is the lag time between when the measurement's actually made and when you see that dot change on the web map?
Well, it's pretty close to real time. I mean, I would say almost instantaneous.
I mean, like 2 or 3 seconds, or less than a second, or?
I think it's less than a second, but actually, it's a good question. We haven't actually timed it. Certainly less than.
It looked like about 2 seconds to me, but anyway, okay.
This is Jen. I'm back on.
Okay.
And I can just briefly talk about projections in ERDDAP.
Yeah.
So that's something that we're going to be working on as part of the Polar Watch project, is coming up with a system for accessing data from ERDDAP using projected data. So you would be ingesting projected data into ERDDAP and then coming up with a system for querying that. So if anybody's interested in that, feel free to email me.
Okay.
The ones that I showed, I'm projecting in Python.
Okay. Alrighty. Anyone else? All right then. Well, that was a lot of fun. So thanks so much, everybody, for joining in there. And you know, if you have if we want to do this again sometime, you know, we could just post something, I think, on the Google group, and maybe we can, you know, get even a wider display of ERDDAP functionality shown. So thanks again, and look forward to the recording. I will post it back to the this interoperability page here if you missed out in the beginning. It'll come in right here, and you'll see a recording link. All right, thanks everybody, and see you around.